Welcome back. Functional Analysis FAV 022 Part 2 of 2 by Professor Dr. A.G. Srinivasan.
The next theorem is on completeness. This is very interesting again. This theorem is very obvious. Theorem will take only 2 or 3 minutes because we have done the similar theorem some time back. Okay. Now, the theorem says as follows. Every finite dimensional subspace Y of a normed space is complete. Now, listen carefully. This is finite dimensional vector space. Finite dimensional normed space. Of course, a subspace. This is going to be always complete. What does complete means? Every sequence, Cauchy sequence converges. So every finite dimensional space is always going to be complete. In particular, that's a result. I'll put in red color because of very important result. Every finite dimensional normed linear space is always complete. Okay. Now we need the following result to prove. We already proved it. It's very easy proof. Recall the same result. We already proved it. Norm of alpha I xi j is equal to I equal to 1 to n is greater than or equal to c positive. Sigma j is equal to 1 to n modulus alpha. I assume result here to prove this. So prove the main theorem. I'm going to prove this theorem now. Proof is very simple, very immediate. We'll prove it now. Every finite dimensional space is certainly complete. Now what to prove? I will take a Cauchy sequence in Y and show that it is always complete. Now proof is very simple. So let us take the proof of the main theorem. Let X be a nonlinear space, Y a subspace of X, such that Y is finite dimensional. Please remember, X need not be finite dimensional, but Y, a subspace, is finite dimensional, and therefore Y is complete. Of course, if you replace X with a finite dimensional, obviously it becomes complete by this theorem. Okay, that's an important point. So to show that Y is complete, I will now take a Cauchy sequence Ym. So Ym is a Cauchy sequence in Y. We wish to show that Ym converges to some point of Y. You know what is the definition of a convergence? We revised it today. What is the convergence definition? And what is the Cauchy sequence? If you want, I'll revise it quickly for 1 minute. I will not take much time. We say a sequence Ym converges to Y if two things happens. One, limit m tends to infinity, norm Ym minus Y tends to 0. And this Y also belongs to Y. Don't forget, the limit also belongs to Y. Where, what is Ym? Ym is a sequence in M. So Ym is a sequence in M. We say Yn converges to Y if limit n tends to infinity, Ym minus Y tends to 0. And not only that, Y also belongs to Y. And what is the Cauchy sequence for revision purposes? What is the Cauchy sequence? We say Ym is a Cauchy sequence. Is a Cauchy sequence. Is a Cauchy sequence if there exists a n such that for every m comma n greater than capital N, norm of Ym minus Yn tends to 0 as such. Okay, and we already saw every convergent sequence is a Cauchy sequence, and if every Cauchy sequence converges, it is complete. That's what we revised it here. So I just revised what is the Cauchy sequence and what is the convergent sequence. Let's come back here to the discussion. So let us take a Cauchy sequence. We are going to show, we wish to prove that Ym converges to some point Y and that Y also belongs to Y. Proof is very easy. Now what is Y? Y is finite dimensional. So I assume the dimension of Y is M. And because it's finite dimensional, there exists a basis E1 to En also for Y. Now because Ym is also in Y, remember Ym belongs to Y, meaning for each M, Ym belongs to Y. And what is Y? Y is finite dimensional. And Y has a basis E1 to En. That means this Ym can be written as a linear combination of alpha 1 E1 plus alpha 2 E2 etc. alpha and En. But because there's a m here, I will put alpha 1 m e1 plus alpha 2 m e1 e2 plus alpha n e1. So this is always possible in a convergent sequence. As an element of a nonlinear space. Now, because ym is Cauchy, by definition of Cauchy sequence, there is a n always such that norm of ym minus yr is less than epsilon for all m comma r greater than capital N. Okay, that is by definition of your Cauchy sequence. So I just taken this. Okay, this is what I'm just taking it. I'm taking it ym minus yr is less than epsilon. Let me write it here. The quick definition, very easy, don't worry. This is going to be ym minus yr is less than epsilon for every m comma r greater than capital N. Now this we will write as epsilon, this is a larger quantity, is greater than norm ym minus yr. Is that right? But what is ym? We already saw ym can be expressed. Maybe I'll change the color. We already saw ym is expressed as alpha 1 m e1 because e1 to en is a basis. Alpha 2 m e2 etc. Alpha alpha n is a basis n. Alpha n power m en. So if you use that context, you will get epsilon greater than norm. What is yn? Sigma j is equal to 1 to n alpha j m ej minus what is yr? Sigma some j is equal to 1 to n alpha jr ej. I think it's clear because it's going to be from ym is in terms of m, yr is in terms of r. That's why written here in a detailed form. You will get it that, and I've taken that ej common because if you see there's an ej common here. Ej is common to both, so you get alpha j m, alpha j power r. So I'm getting that here. So we'll get epsilon greater than ym minus yr is equal to sigma j is equal to n alpha j m minus alpha j power r ej. But result 1 says the norm, the norm is greater than or equal to c times modulus of the scalars. So using that property, I'm going to write here greater than or equal to c times sigma j is equal to 1 to n, the modulus of the scalars. The scalars are alpha j m minus alpha j r. And of course, certainly it's needless to say c is positive. This is for all m comma r greater than r. So epsilon is greater than or equal to c, j is equal to 1 to n alpha j m minus alpha j power r. Right? Now, I will again write this. So epsilon greater than or equal to this. Let me write it here and just explain the step. So epsilon greater than, let me just check it one more time whether I'm writing correctly. I don't want to mix. Yeah, it's going to be, this is going to be sigma j is equal to 1 to n, etc. What I have done it here is greater than or equal to c times sigma j is equal to 1 to n alpha j power m minus alpha j power r. Okay. Now, of course, modulus is there. Don't forget, modulus is there. Now, next step is a very crucial step. Listen, take one element alpha j power m minus alpha j power r. The modulus is always a positive quantity. This is always smaller than sigma j is equal to 1 to n modulus alpha j power m minus alpha j power r. This is a single term. So modulus a1 is less than or equal to modulus a1 plus modulus a2 because modulus is always positive or non-negative. So individual term is always smaller than adding more than one term to that. Okay. So you observe that one second because norm is a positive real quantity. 1 second, I'll join. 1 second. I got my call cut. Just a minute. Yeah. So what I try to say is that the individual norm is less than or equal to sum of the norms. So alpha jm minus alpha jr is less than or equal to this. But this is nothing but this, which is less than epsilon by c. Can you see that? Of course, c is positive, don't forget. Epsilon also is positive. So this ratio is also positive. And because epsilon is very small, I can talk this as some other quantism delta. So what I showed now is alpha j power m minus alpha j power r is less than delta, but delta is positive for every m comma r greater than n. What does it mean? It means that alpha j m is a Cauchy sequence because it is less than delta for every m comma n greater than r. So this alpha j power m is a Cauchy sequence. And what is alpha j power m? Is always belongs to r or c. They are scalars. And both r and c is always a complete metric space. And therefore, every Cauchy sequence converges. And hence, alpha j power m converges to alpha j. And even that alpha j belongs to that r or c, depends on your field. So alpha j is a Cauchy sequence. This is what guarantees here. One second. Alpha j is a Cauchy sequence. You know very well about it. And it converges to a point in R or C because R as well as C is both a complete metric space, right? That's what I've done here in my explanation. So you can see that alpha j power m minus alpha j power r is not equal to sigma j is equal to 1 to n alpha j power minus alpha j power r, which is less than epsilon by c. Epsilon is positive given. If c is also positive, the ratio is also non-negative. And you can always fix a small number as you like as delta. So alpha j power is a Cauchy sequence in RRC is always complete. Hence, it's also a convergent sequence. So alpha j power m converges to alpha j. I think it's very easy to prove. Now, what is important is that this alpha j is also in Y. You know why? Because alpha jm, okay, is a scale. Sorry, not in Y. It's a mistake. Sorry, it's not in Y. It's in R. I just erased this. Sorry. It's not in M. This is going to be in R. So alpha j belongs to either R or C, right? Or C. Or C. The real numbers are complex numbers. So alpha j is a real number or a complex number. It belongs to R. So for each alpha j power m, we get an alpha j. If m is fixed, you get alpha j1, you get an alpha 1. If m is 2, alpha j2 is another alpha 2. So you can find like that for each m, you can find alpha 1 because j, j running from 1 to n. I can find n such limits. I will now construct my new y as y is equal to alpha 1 e1 plus alpha 2 e2 etc. alpha n e1, where alpha I belongs to R. Now, e1 to en is a basis for y, and alpha 1 e1, alpha 2 etc. alpha n en belongs to y because it's a finite-dimensional vector space. Therefore, this y is certainly belongs to y. Yeah. Moreover, we take norm ym minus y. We'll take norm ym minus y. That is equal to sigma j is equal to 1. What is ym? We already saw alpha j power vj. And y, if you take, is going to be alpha j ej. I have taken ej common. This is less than or equal to by triangle inequality. J is equal to 1 to n alpha j power m modulus alpha j into norm ej. But we already saw that this converges to this. Therefore, this becomes 0. This becomes 0. This becomes 0. Therefore, norm ym minus m tends to 0. That means ym converges to y. So ym converges to y, first point. Well, let me write it here. Ym converges to y, first point. Second, see here, y belongs to y. We already said it. Y belongs to y. And what is y basically? Ym is basically a Cauchy sequence. Ym is a Cauchy sequence in y. So what is ym? Is a Cauchy sequence. Let me write it here. Ym is also a Cauchy sequence. Is a Cauchy sequence. Of course, in y as well. So ym is Cauchy. Ym converges to y belongs to y, that means y is complete. That's we proved y is complete. Now, this shows that in a finite dimensional vector space, it is always going to be a complete space. So if it is a finite dimensional vector space, a non-linear space, it is always going to be complete. It's going to be always a Banach space. It's always going to be a Banach space. You don't have to even prove it. I think as I told you, I'm going to show next class that every finite dimensional vector space, non-linear space, is going to be complete. Today, we proved it. Now, suppose I replace x. Now, in this theorem, what is x? X is actually a non-linear space, need not be finite dimensional. But what is important is why a subset of x is finite dimensional. Suppose x is finite dimensional, suppose x is finite, I'll write it here for you. If x is finite dimensional, then obviously x subset of x is always true. Therefore, being a finite dimensional space, it's going to be complete. So every finite dimensional non-linear space is complete. Or equivalently, every finite dimensional non-linear space is a Banach space. Every finite dimensional non-linear space is a Banach space. Okay, that's a theorem we already proved it. Okay, now let's go to another interesting theorem. The theorem is only theorem already proved. Maybe I can show you that theorem also in 1 minute. A subspace M of a complete metric space is itself is complete if and only if the set M is closed. We already proved in theorem, I think theorem 1.47. I think we proved in one of the lectures. I think FAV 018. I'm not sure about the lecture number. A subspace is a complete metric space if and only if M is closed. So in that context, every finite dimensional vector space is the non-linear space is always complete. Therefore, it is always closed. Every finite dimensional space, a non-linear space, is always complete. Therefore, it is always closed, because every non-linear space is complete if and only if it is closed. Therefore, every dimensional space, finite dimensional space, subspace Y is closed. So if you take a finite dimensional space, it is always closed, it is always complete, it's always a Banach space. That's what we explained to you here. Okay, and the last class we have defined what.
This is Professor Dr. A.G. Srinivasan. Thank you.